also considered a homogeneous reaction mixture. That means all the reactions take place in a single phase, so all the components are in the same phase. Now the criterion for equilibrium is K equal to 1 to C. Mu J, C. That means these are the stoichiometric coefficients. This is of course the chemical potential that we know. So these have to add up to C. This is really not a sum, but actually because some of the stoichiometric integrity will be negative. Right? But the convention on the stoichiometric coefficients is to write this as a sum. Otherwise, you have to collect all the terms on the reactant side and equate it to the terms on the product side, which is anyway what we finally will do. But for convenience, when you're treating a general reaction mixture, this sign convention is very useful. The whole confusion in reaction equilibrium arises from the definition of the activity which involves the somewhat vaguely understood standard state. So first, this is clearly corresponding to the chemical potential of component change, the mixture. It's very clear from the context, but we need to be clear to emphasize that. So the first definition is that the activity of a species J in a mixture is defined to be the exponential of the chemical potential of that component minus the chemical potential of that component in some unspecified or left unspecified. Finally, we have to do the calculation, we have to specify. But it's sort of left open, and this is the standard state. Left open because when there is a choice, we should make the most convenient choice. We'll see how to make that most convenient choice. But most important is this is of course dependent, this has everything to do with the reaction mixture. Right? So this is a function of the temperature, pressure of the mixture and also the composition of the mixture. But the convention says that the standard state can be either a pure component or a mixture. If it is a pure component, then we have mu K S S. Pure component means mu K S S depends on two variables only, namely the temperature and pressure, which are the most convenient variables. And so here, the temperature will be the temperature of the reaction mixture. The pressure has to be some standard pressure. Whereas if you are choosing a standard state, which is a mixture standard state, right, then the mu G will have to be determined to specify it unambiguously, and it specifies temperature, pressure as well as the composition of the standard state, if it is going to be a mixture standard state, in which case only the temperature will be the temperature of the reaction mixture. Pressure you have to choose some standard pressure, and also the composition has to be some standard. These have to be specified. These are very important conventions that you have to keep in mind. There is nothing very fundamental about it. It has emerged due to convenience and various reasons, which we will see why it has emerged here this time. So now, when we want to use this equation and express it in terms of the activities, right? So then I have to rewrite the chemical potential of a component G in the actual mixture as that of the standard state of that component. So then we substitute it into this, we saw that we will get the following equation, namely logarithm of Ka is equal to minus 1 over Rp, sum over J equal to 1 to C. The Ka is defined as y, that is a product, J equal to 1 to C, Aj mix raised to the power product taken over all the components that constitute the reaction. So now you look at this, and AA is given, definition is given, right? Now, can you tell me, just forget about the right hand side, just focus on the left hand side. What is the function of which variables does Ka depend on? Temperature, it depends on. Does it depend on the pressure? No. You have to set aside all you know about the equilibrium constant and tell me, without looking at the right hand side, just look at the left hand side, Ka. Ka is, so you are having a problem doing it, then I just erase this. Now you look at this and tell me, calculate it. So I just say calculate Ka. So what are the variables I need? Obviously the temperature, the pressure, and the composition of the mixture. And I also have to be specified the standard state pressures and composition depending on what standard state I have chosen. It is a function of both all three, temperature, pressure, and Z mixture, and also a function of the standard state. And first thing you have to recognize that I can choose different standard states for different components. We will see that shortly. Now if I look at the right hand side, if I can emphasize that, I can even put here J, but it is understood. Corresponds to the standard state chemical potential of the J component, which means I can choose for the J component, I can choose some standard, some other component, I can choose some other standard state. Now look at this and tell me what does it depend on? The temperature alone, because if for a particular component J I am choosing the pure component, then temperature is the temperature of the reaction. Vss has nothing to do with the pressure of the reaction. It has to be given. I have to specify that. So, body temperature is a variable. Now, if for instance one of the components has a mixture standard state, then also the pressure and the composition of that standard state has to be specified. We have to say what it is, 1 bar or 10 bar or whatever, and particular composition. So once I do that, the right hand side depends, you can clearly see, only on temperature. So even the Ka inherently, by definition, depends on the temperature, pressure, and the composition of the mixture. The criterion for equilibrium, because we get this Ka independently can be defined and we can look at it. Clearly depends on temperature, pressure, and composition of the reaction mixture. But the criterion for equilibrium makes it equal to a quantity which depends only on temperature. So what is involved? One is the criterion for equilibrium, and also the way we have chosen the standard state, the convention. For instance, somebody can say, why should I choose the pressure to be 1 bar always? I choose the pressure of the standard state also to be the pressure of the mixture. Then Ka will become a function of the pressure as well. Only the convention that makes it dependent only on the temperature. So there is nothing fundamental about Ka depending only on the temperature. It is purely, partly it is fundamental in that we are making use of the fundamental criterion for chemical equilibrium. But on top of it, it is also the convention which makes the Ka depend only on temperature. So from this side, looking at the right hand side, I can conclude that Ka is equal to, or is a function of temperature alone. So now looking at this, the famous equation that is often written without giving much thought is this. So now first thing we have made it clear what this K is. This K has to be Ka. And then we also see that we can get from this, if I choose the pure component standard state for all species. That's very important. Then only I get the free energy change of reaction, right? So, like this is a very important property of KA. So we have to keep that in mind. Pure component standard state for all change. Then I can write this as minus 1 over RT, sum over J equal to 1 to C GJ SS. And then this can be regarded as the standard free energy change of reaction. Now, of course, again, confusion often arises because delta always indicates a change, a difference, right? On the other hand, what you're seeing is a sum. So does it make sense to use delta to represent the sum? Does it or does it not? Make sense or doesn't make sense? To use delta to denote the sum. Why does it make sense? Some of them will be negative. At the same point I made there, because if you, for instance, take the reaction like this, clearly this quantity, let's write this one, the 4 components here, right? So this will be clearly C times dC SS, assuming that I have chosen the pure component. Otherwise, chemical potential will not be equal to the Gibbs free energy. Whereas the minus A so it is a difference, right? But it's sort of conceived by, it's convenient to write it as a sum and then forget about it when you do the theoretical development. When you come to practical calculus, for instance, same thing here. This looks like a product, but clearly this is going to be always have a numerator and a denominator. For instance, to write this would be AA. I'm sorry, call it AC raised to the power C. This one, this product is actually going to look like this. It's in fact easier to, if you remember what it is, it's easier to write it in actual situations than to put all this pi and other things, right? So you will easily, all of you know how to write the equilibrium constant of a reaction. And so this would be AA. So this is how it would be, the product pi I equal to 1. This is a very general reaction, right? So if you know how to write. Now we looked at 2 different standard states most commonly used for the pure component, right? One is the so-called ideal gas standard state. So by standard state 1, right? So this would mean that uj standard state is equal to uj, the ideal gas associated with the species. We saw that even though a particular species might behave in a certain way at a given temperature and pressure, we could always associate the fictitious ideal gas associated with that component at any temperature and pressure in fact. Now the standard state, which we will call the standard state 2, is like 1 here. If I choose for J the standard state 2, then this would become simply the pure component. So this is clearly a gas, it's an ideal gas. This, it depends on whether the actual substance is a gas or a liquid actually. The temperature of the reaction mixture and at the standard pressure that you have chosen, which is always invariably 1 bar, but I'm just leaving it open so that you're not always constrained by that. So that is what it is. Now, as I have said, I can choose a different standard state. Let us say I now restrict myself to one of these two standard pure components. Then only I can use the G. So it is entirely possible that I could choose for A the ideal gas, the B the pure component, and C the ideal gas, and D the ideal gas. I can do that. Further, one of the common rules given in some of the textbooks is that if it is a gas phase reaction, you choose this. If it is a liquid phase reaction, you choose this. There is nothing like that. If reaction could be a liquid phase, I have every right to choose the ideal gas standard state for all the species. So it is entirely a choice, because if it is going to be dictated by the phase of the reaction, then there is no question of choice, right? So these things you have to keep in mind. Right? So now having done this, we have now established that with all these conventions, K is a function of temperature. Now it's important to ask the famous Hoff equation, somewhat looks like the Clausius-Clapeyron equation. Is we can ask, so we are going to be restricted only to these two steady states, standard states now. So we can ask what is the derivative of the two important points. The choice is, of course, I can choose a mixture standard state also for some of them, but if you restrict to pure component, each component standard state is not dictated either by the phase of the reaction mixture or the standard states of the other components. Entirely my choice or your choice. So what is this? We can also, we just have to differentiate this with respect to temperature. Very important to remember that the pressure here is fixed, so it becomes a function of temperature alone, the right hand side. That's how we established that. So I'm not going to integrate, differentiate this. This is obviously a mess. It's a function of temperature, pressure, but I know the criterion of equilibrium says that this is equal to this. So I'm better off just differentiating this with respect to temperature. So when I do that, I will get the famous Hoff relation. So first thing is sum over K equal to 1 to C times, I can maybe take minus 1 over R as a constant. Minus 1 over R can be taken outside. I don't want to deal with the negative there also, because we have to deal with negative anyway. So I have to now differentiate 1 over t, which is minus 1 over t squared. That's the first term I am writing. So I am taking the sum. Minus 1 over R is taken out. I have to differentiate 1 over t with respect to temperature, which is minus 1 over t squared. Next I have plus 1 over t. And then I have to differentiate this with respect to temperature. So this is a derivative of a sum. It can be written as sum of the derivative. So I take it inside the sum. And I know the mu j's are constant. So I have to only differentiate this. So then I get sum over j equal to 1 to c d g j standard state, which is a function of temperature alone. I can put d by dt because the pressure is chosen, so it is fixed. I can write it like this. So what is this? Minus the entropy, right? So minus the entropy is very important. Again, it will depend on the temperature. dG by dt is minus S, right? dG is minus S dt plus B dV. So this is minus Sj TPSS. It's very important. So always important to put the arguments clearly, right? So I have that. So now I can now take. So what I do is I will take a minus 1 over t squared outside. So that I get 1 over RT squared. You can see how this will become the standard enthalpy change of reaction. So minus 1 over R and minus 1 over t squared I am taking out. So let's, for the first term, that is the straightforward thing to do. So let's write it term by term. So 1 over RT squared sum over k equal to 1 to c first term, right? So then I have minus 1 over RT sum over J equal to 1 to C times minus Sj what I have here. So I want to combine these two terms. So I have a minus 1 over RT and then a minus, so this can be made into a plus, and then I want to obviously combine these two terms. So I can take a 1 over RT is quite common for both, and then sum over K equal to 1 to C, or maybe I can write it to make it clear. I can write it as 1 over RT squared times T Sj. Right? Multiply and divide the second term both by the temperature. So when I do that, I have 1 over RT squared times, and then you will clearly see now the enthalpy will come in. Sum over J equal to 1 to C, because J is a constant coefficient, not a constant, it's a coefficient in both of these sums. And so I get TJSS plus TSJSS. Clearly evaluated at the temperature of the reaction mixture and the standard pressure, and this is G plus Ts is H. Right? So then this is 1 over RT squared times SS this I may call as the standard enthalpy change of reaction. The standard enthalpy change of reaction. Again, it's an enthalpy change because some of the stoichiometric quotient will be negative, so it will look like a difference. So that is the enthalpy change of reaction. Evaluated at the temperature of the reaction. So clearly the right hand side also has to be a function of temperature alone. And so the famous relations depend on the choice of the standard state being pure component, maybe K to the exponential minus delta G, not by RT. We made it very clear what the not actually means. Right? And further, the Hoff relation, which gives an expression to the derivative of the logarithm of Ka. Standard enthalpy will also fall into place only when we choose for all components the pure component standard state. It is more or less the convention in many cases. So this is what we have. Now you can see that if, for instance, I choose SS1 for all the components, then this can be replaced for all the components, let's say. Convenience, I do that. Then we know that this is a function only of temperature, because ideal gas enthalpy is a function. We don't need to specify the pressure. It is independent of the standard question. So I need only the temperature to evaluate the standard. It is function of temperature. But if I, for instance, choose this, the second for all the components, then it would be a function of both temperature and the standard state pressure which I have to provide in order to calculate the standard enthalpy change of reaction. Of course, it's always possible. For some components, I can choose the ideal gas standard state, and for some, the pure component standard state. So, a lot of it has to do with convention. It is very difficult to write general expressions since there is so much of choice. Right? So, we have to restrict ourselves to a particular choice, as in fact we have done. Restrict to the pure component, we get all the standard relations involving the equilibrium constant. Are there any questions? So let's now look at what would be or what would be activity, because we are focused on this. So this is what we will get from the tables. The tables, maybe we should set up the overhead related model. You can also go and look at the tables. Right? We will explain how to get calculation. So typically what will happen in a calculation is that the temperature of the reaction mixture is given. So let's say I want to calculate the equilibrium constant of some reaction, ammonia formation or whatever. Right? So first thing you would do is you calculate the right hand side. That is what is available from tables. You see how to calculate it from tables. The right hand side. Now what about the left hand side? We have to complete both the parts of the calculation. The right hand side numerical calculation from the tables. Now what about the left hand side? We haven't yet stated what is the final objective. Final objective is to calculate the composition of the equilibrium mixture. What will be the composition at equilibrium? And we'll see how that's a real problem facing for a single reaction or for multiple reactions. What is the composition of the mixture at equilibrium? That's a basic problem. So for that, we have to use this equation, and right hand side getting it from the table. We'll see how to do that tomorrow. Maybe at the beginning of the class we can set up the overhead projector and I will show you how we implement the tables, because the tables has a set of convention, most of which were stated in the tables, but there is a certain discrepancy in the notation between what I have used and what is there in the table. So I will say how to connect the terms that I have, the terminology and the notation that I have introduced here with what you find in the tables. It's fairly straightforward. So we will do that tomorrow. But today we will now look at what is the activity, because I have this, that from the tables. Now this depends again on the standard state, whether we choose one or two. So restricting ourselves to just the pure constant standard state, let's see how to calculate or express the activity. What we want to express it is in terms of the fugacities, because the fugacity is what we can estimate from an equation of state, fugacity or fugacity coefficient. So that's what we have always done. When you look at vapor liquid equilibrium, we've always dealt with fugacity rather than chemical potential. Of course, here I have introduced the activity through the chemical potential, just as we introduced the activity coefficient through the chemical potential. Finally, we have to relate it to the fugacity. Now that depends on what is the standard state we choose. So first I take the standard state 1 and see how the activity of a particular component in a mixture depends on the fugacity of that component. So that is fairly straightforward. It's again a question of adding and subtracting a few chemical potentials. So we'll see how another example of how to do that. So let's take let's calculate first mu J mix minus mu J SS1. So for that I need to make it explicit. So it's always better to see. So this would be mu J mix PPZ. These all correspond to the temperature, the pressure, and the composition of the mixture. I haven't put mix everywhere. It's very clear from the context. When I say mu J mix, it's the actual J chemical potential in the mixture, corresponding to the mixture conditions. Right? And the other one is mu J. Now this is IG ESS. We want to get the fugacity of the component J. What should I subtract first? What is the definition of the fugacity of what chemical potential does it involve other than the actual mixture chemical potential? When you wiggle it, you should know the ideal gas mixture chemical potential, the same temperature, pressure and composition of the mixture. So that's the first thing I would subtract. Minus G, so I'm taking G. So when subtracting, obviously I have to add that. And then I have the this. So this is easily expressible in terms of the fugacity. It is in fact RT, because the fugacity, if you recollect, is P exponential of mu j minus mix minus mu j ITM evaluated of course with the same temperature, pressure and composition divided by RT. So this difference is going to be take it over here and take the logarithm and then multiply by RT. So I will get that. So this will be RT logarithm. Now what about this? This we know how to write the property of the ideal gas mixture. We know that the defining equation for the chemical potential of any component is equal to plus what? Plus RT log Zi. We used Yi earlier, but here we restrict this. Here the actual mixture can be anything. It need not be a gas, can be anything. RT log Zi minus I'm sorry, J actually, because we are looking at the J component. Now what about this difference? We have almost got to the answer. So this difference, mu j Ig dP, this difference, this one. Integral of d, this is nothing but, let's write this here. That difference is clearly a difference between two ideal gas states of the same component, the same temperature, only the pressure is different. So we know how to do that as an integral. Is equal to where we integrate from PSS to P. So I'll put this as P prime, P prime. P prime is a dummy date because I have P here, so I put. Now what is this? This is clearly the volume, specific volume of the ideal, like RT by P. So there is the RT log P by PSS. So I can now write this difference. So I have an RT log Zj and then I have an RT log P divided by PSS. So clearly the RT log, there is an RT log P. The P is still the denominator. So that is going to cancel with this RT log P. So this is RT log P. This is actually minus RT log P because P is the denominator. Again I have minus RT log Zj. So that is going to cancel with this. Right? So what do I get finally? All I have is RT logarithm of Fj mix. This is there. Right? So this whole thing is equal to RT logarithm Fj mix by PSS. Right? Because that is in the denominator. So now, what do I have? So what does this mean? So I have Aj mix is exponential 1 over RT of this difference. So 1 over RT will cancel. So I have exponential of the logarithm of Fj mix by PSS. The exponential logarithm will give me unity, right? So this will be Fj mix by PSS. This is for standard state 1. So for the standard state, the activity doesn't have any units. So fugacity has units of pressure. This is very important because many books tend to ignore this because they say we are taking it to be 1 bar. So So P is 1. That means you have to remember that the fugacity has to be expressed in bar, right? So you have to, first of all, the standard state pressure need not be 1 bar. Why should we restrict it? We know that's the convention. Right now we don't have to restrict it. And why should we, even if we do, why should we restrict the units for pressure to be bar? There's no need to do that. So this is very clear, it makes it very explicit. This is independent of what our other conventions, what the standard state pressure commonly chosen, or what units is expressing, we don't care. Clearly, when you want to use this equation, both this and this must be the same units of pressure. This is very clear. Now, I will leave it as an exercise for you to show that the AJ mix for a component A, if I choose the standard state 2, it is actually will be Fj mix by Fj, the pure component fugacity, evaluated the temperature of the reaction mixture, but the standard pressure. You have to prove it. I leave it as an example. Doing very similar steps, it will be an interesting exercise for you to prove that. Again, have to do the, pretty much this step is there, but only now you don't have Uj Ig, but you have Uj at TPS. So you have to figure out how to handle that. You've already seen how to do that in many cases. So these are two very important expressions. Now we will look at how the Ka looks. Right? We will now, for convenience, choose the ideal gas standard state for all the components, because you will find, for one thing, it's convenient, even if, as I said, even if the actual reaction mixture is a liquid phase, there's nothing that prevents me from choosing the ideal gas standard state for all the components. Right? So the actual liquid phase will influence when we calculate the fugacity of the component. This is the actual this is what I'm getting out of the convention of the ideal gas standard state. But where the phase of the mixture, because you might say, that is open to choice, then how does the phase of the reaction mixture influence the calculation? The phase will influence, because this will depend on whether it is a liquid mixture or a gas mixture or whatever else it is. Right? That is the actual, this is where the actual reaction. So what you find here is that while the condition of equilibrium is all at the temperature, pressure and composition of the reaction mixture, at equilibrium only it is valid. Right? However, by defining the activity and writing it as the same equation as logarithm of Ka equal to whatever, what we are doing is that we are now splitting it into two parts, and both parts have a certain portion of the actual reaction mixture, right, and a certain component of the standard state. So neither Ka nor the standard free energy change is entirely determined by the reaction conditions alone. Both require or depend on the choice of the standard state. But there is also a component corresponding to the actual reaction mixture. For instance, on the right hand side is the components in the reaction plus the temperature of the reaction mixture. That will determine how to calculate the right hand side. So the left hand side, we of course, because the fugacity is involved, will depend on the, that is where the pressure comes in. Because you might wonder if Ka is dependent on temperature, then does it mean that the reaction equilibrium is independent of pressure? No, because the dependence of pressure is sort of shifted all in to the left hand side. When I am calculating this, I need to know not only the temperature but also the pressure, and of course the composition of the reaction mixture, which needs to be found. Right? So, are there any questions? What has been covered so far? Now what I am going to do is, as a concrete case, I take the standard state 1, right, for all the components in the mixture and see how the Ka looks like, because this will now lead to a whole host of other equilibrium constants which you might all be familiar with, namely the mole fraction based equilibrium constant, the pressure based, partial pressure based equilibrium constant, and so on. Let us see how those come, but the basis for all that is the activity based equilibrium constant. If you have ever in doubt which equilibrium constant in a particular book, it can correspond to it just using K. You have to always go back to KA and the relations governing that and see under what conditions you get the other ones. Right? So let's now look at what KA is for standard state 1 chosen for all the species. So KA we have seen is pi I equal to 1 to C AJ makes. So now for standard state 1 for all J, I get pi J equal to 1 to C if J makes divided by P standard state. Right? So now I can write this as we will first get the fugacity-based equilibrium constant. So we get pi J equal to 1 to C if J makes that is what I have here. But there is also 1 over PSS. It is conveniently forgotten if the pressure is chosen as 1 bar, but we don't want to do that. So PSS, right? Pi J, what is pi J equal to 1 to C? 1 over PSS. Because it's the same quantity, right? So I have, for instance, if I have this reaction A plus B, always better to fall back on a familiar particular reaction. So what would this be? And it would be 1 over PSS power D times PSS power C times PSS power minus A and PSS power minus B. It would be 1 over PSS raised to the power C plus D minus A plus B. It is the same quantity, it is raised to different powers and you take the product. This is what we will get. So now in the general case, I will write this as PSS raised to the power delta mu. That's a symbol commonly used. What is delta mu? Delta mu is D plus C minus A plus B. For that particular reaction, that is where you get the delta, right? But I can generally write delta mu, define it as J equal to 1 to C product mu J. So the sum, if the sum over all components, I take only the ones that are on the product. Now if you confuse, I don't have to put A equal to 1, I will just put J. So this is the sum over all J on the product side minus all J on the reactant side have a negative. So if I'm going to put the minus here, so then I would have to take the modules, which is exactly what I am doing here. So I take C plus D minus, I don't consider now the signs, I will just take the absolute value because I am subtracting. Right? So that is why this is the way it is written, delta mu. So I can now write this as KF by PSS. This is for standard state 1 for all J, that you have to very much keep in mind. You can change the standard state, and as I said, for one component, if you choose one standard state, another component, another, the whole thing will become very difficult to write in general. So, write the most common choices. So, let's now further. So, we're almost running out of time, but since I know that by definition, I can write Fj makes. Now we introduce the fugacity coefficient because that is where the all non-idealities contained. Right? So Fj makes, we see that Pzj phi j makes purely by definition of the fugacity coefficient. We define the fugacity coefficient so that for the fugacity coefficient for all the components will become 1 for the ideal gas mixture. Right? So then what will Kf be? Right? So Kf would be phi j equal to 1 to Cp Zj phi j makes, right? Which now can be written as, we have already seen what P phi would be. It is going to be P times delta mu Kp Well, I write this as P set J as a partial pressure. So I can write this as further as Kp times K phi. The Kp is the partial pressure based equilibrium constant. So it is just a product. So I can write it as two products. I can split it into two products. Phi j equal to 1, so this can be written as phi j equal to 1 to C P set J. And so this Kf would be raised to all raised to power mu K. And so this would be times phi j equal to 1 to C. I can only split the product. Phi j mix. So this I can write it as Kp times K phi. So I can put that there. Right? So this can be written as Kp times K phi. Further, if we want to write it as a mole fraction based equilibrium constant, clearly this would be P times delta mu times Kz times K phi. In which case this would become P over Pss raised to the power delta mu times Kz times K phi. So we have now introduced, we have got Ka first, we've got Kf here, we've got Kp, K phi, Kz. There's also Kc, which is related to the concentration, which we can bring in later if required. So these are all the other equilibrium constants come into play. The basic is Ka, and then we have the Kf and K phi and Kz. It's all a question of definition and how you want to write the Ka. Right? So we've got all this. Then, so now important simplification. If the actual reaction mixture is an ideal gas mixture, let's say it's a gas mixture. Now the actual condition of the reaction is a gas phase, and the mixture behaves like an ideal gas mixture. Clearly, this is equal to 1 for an ideal gas mixture. That's probably the only case we take up for calculation when we get to it. Right? So then the whole thing becomes simplified. We get the mole fraction based equilibrium constant from which we can get the composition of the reaction mixture. Otherwise, you have to calculate the fugacity coefficient. Calculation will be much more difficult. So we run out of time. So we will take this up tomorrow and look at how to calculate or do an actual calculation